Lab this week was about constant velocity. Within this lab, we recorded a video of an object in motion with constant velocity. The object in this case was a cart with wheels. Along with that, we also coded a program to simulate an object with the constant velocity. Using the data gathered from both sources, we could compare the video data to the predicted model to answer a few different questions. For us to compare the two models, a few underlying concepts are needed. First is that an object with constant velocity means it has a net force of 0. We also need to figure out the velocity and position of the object at different points in time. We do this using two different equations. The first is Vf equals Vi plus F net over m delta t. This is the final velocity equals the initial velocity plus the net force divided by the mass multiplied by the change in time. The next one is Rf equals Ri plus Vi delta t plus F net over m delta t squared. This is the final position equals the initial position plus the initial velocity multiplied by the change in time plus the net force divided by the mass multiplied by the change in time squared. Since we know the net force equals 0 and the velocity is constant, we can just use Rf equals Ri plus Vi delta t, which is the final position equals the initial position plus the initial velocity multiplied by the change in time. From the video, we used Tracker to find different points in time as well as the location of the object at those times along the x-axis. The table and graph are different points in time and the corresponding position. And for the graph on the right, there's a slight change in the angle of the graph, which is due to human error. For the predicted data, we used GlowScript to create a program that would simulate an object with the same Fnet and velocity to find the predicted position of the object if everything were to go exactly as planned with no errors. And in this case, the slope of the line, the line is completely straight. Using Tracker, we found the time and corresponding position of the object, which in this case was the cart on wheels. The only problem with gathering completely accurate data was that the camera positioning was slightly at an angle, so the recorded position at different times was a little off. So as you moved farther to the right because of the angle, the position became a little skewed. Along with the camera, there's naturally still a little bit of friction within the wheels of the cart, but not enough to make any significant difference within the data. For the coding, the formulas mentioned earlier were used to calculate the data more accurately. Using a loop to repeat the process over and over without having to do the calculations individually, a more accurate model of how the cart should have moved can be produced. The velocity and position were updated using those formulas as well. And the snippet of code on the right is the loop that we used to calculate the change in position and velocity. To wrap up, throughout the experiment, we had our positive x direction being to the right. If we were to have flipped it so that our positive x was to the left, everything would essentially be the same except the sign of all the values would be flipped. So if we were to have had the x direction, positive x be to the left, but continued moving the cart to the right, the distance would have just been negative and then the velocity would have just been negative. If we were to move it to the left in the new positive x direction, the values would be exactly the same as the ones found. Along with that, the net force was set equal to 0, meaning there's a force from the table countering gravity, which is force normal, setting the y component of the force equal to 0. And then for the movement and the force in the x direction, the constant velocity by definition means F net equals 0. But since the cart was moving, there was an initial force that caused it to move, which was us pushing it, and then stopped acting on it, which then let the cart move freely in a straight line, resulting in the constant velocity.